All right, in this video, we're going to do example 5, which is based on a Hughes-Hallett problem in section 1.4, number 25. And again, I'll start by reading at least up through part A of the problem, and then we'll go on from there. A company produces and sells shirts. The fixed costs are $7,000, and the variable costs are $5 per shirt. Part A, shirts are sold for $12 each. Find cost and revenue as functions of the quantity of shirts Q. So in this part, we're just doing cost and revenue functions. In some of the other parts, we will combine that with supply and demand and do something different. But let's start simple. So part A, we're going to have a cost function, C of Q. And again, this is going to be a linear function. So it's something like mx plus b, but of course we're changing the letters. So instead of m, we'll have some number. Instead of x, we'll have q. And instead of b, we'll have a number. The number that represents slope is the variable cost, and you can tell that again because it's $5 per shirt. And so the units there are telling you that it's a slope, it's a rate or a ratio of dollars per shirt. So anyway, that's the variable costs, 5Q, and the fixed costs are the amount that the company that it costs the company before they ever make any shirts. So it's right before you start making it, like you've bought all the fabric and the paint and the machines or something. So it's the fixed costs, and that's 7,000. So that's the cost function. Let's see. Shirts are sold for $12 each, so that's what we need to know for the that's the price, and that's what we need to know for the revenue. So revenue of Q. Again, this is a linear function. It is something of the form mx plus b. But of course, I put that in quotes again because it will actually be a function of Q. And then the revenue per shirt, which is how much you make per shirt. Again, that's the slope, dollars per shirt, and that's 12. And there is no b in this case, or b is equal to 0, because there's no, you don't make any revenue before you've made and sold your first shirt. So it's just 12Q. So those are my two answers for part A. Okay, part B. The company is considering changing the selling price of the shirts. Demand is Q equals 2,000 minus 40P, where P is price in dollars and Q is the number of shirts. What quantity is sold at the current price of $12 and what profit is realized at this price? So now we're going to go from the price to figure out how many shirts are sold, that is the demand, and then go from that to figure out what the revenue and the cost are and therefore the profit. So we're going to combine all of those. But one step at a time. Let's start with Q. So Q is equal to 2,000 minus 40P. And now they didn't use function notation, but this would have been a nice place if they had used it because they're telling us use this formula and plug in P equals 12, which in function notation you would say something like Q of 12. So this is at P equals 12, so I'll plug that in. 2,000 minus 40 times 12, which is 2,000 minus, and then 4 times 12 is 480. And I guess that's, what, 1,520. I'll probably need my calculator in a minute, but so far I could do it without my calculator. Okay, so that's the quantity that is sold. And now, combining this with part A, we can figure out what the revenue and the cost and therefore the profit is when we sell that many. So we would have, let's see, cost of 1,520 is 5 times 1,520 plus 7,000. And now I will use my calculator. Okay, so when I plug that into my calculator, I get 14,600. Now similarly, I'll have revenue as a function of 1,520. That's equal to 12 times 1,520. and that's equal to 18,240. And finally, profit is equal to revenue minus cost. So that's 18,240 minus 14,600, and that comes out to be 33,640. Okay, and so that's my final answer for part B. Okay, part C is going to take the same idea that we just did in part B, but generalize it. So in part B, we used a single value of price to calculate quantity, and then from that we calculated profit. But now we want to look at profit not as just a single number when p is equal to 12, but we want to look at it as a function of the price. So in other words, if we consider change in the price, a little up or a little down, how will the profit change? And so we're going to rewrite everything as a formula involving price. Okay, so first thing I'll do is I will rewrite the cost and revenue as function of price and then combine them into profit. So let's see. C of Q, we knew from up above, was equal to 5Q plus 7,000. But now we're also going to combine this with the fact that Q is equal to 2,000 minus 40p. And so we're going to take that and we're going to plug it in to the formula. In fact, we're going to plug it in right where there's a Q. So C as a function of P is equal to 5 times 2,000 minus 40p plus 7,000. So I've replaced the Q in the old formula with a formula that has P. And so now I have C as a function of P. Okay, this simplifies, which I'll go ahead and do, to 17,000 minus 200p. And then similarly, I'll do something just like that with revenue. So revenue as a function of Q, it's not going to be 12 times Q, although it was up above. But remember that 12 that we had in part A, that 12 is now changing. It's going to be a variable P. So R of Q is going to be P times Q. Let me erase a little stray mark there. P times Q, which is going to be P times, and then I'll replace Q, 2,000 minus 40p. And again, I can rewrite this and simplify it a little bit. So this is 2,000p minus 40p squared. And I should change also, I made a small mistake the way I wrote it. This is not R of Q, this is R of P. So I'll delete the Q and write a P there. Okay, well finally, profit as a function of P is still revenue minus cost. So it's 2,000p minus 40p squared minus 17,000 minus 200p. And again, I can simplify that. So this is negative 40p squared plus 2,200p minus 17,000. Okay, and that's my final answer for part C. So that may seem like a lot of work, a lot of algebra, makes my answer look worse instead of just a number, but the point is this is how companies can then make predictions or optimizations and figure out the best place for them to be. So in part B, the company, I guess, essentially figured out where they are right now, like how much money are we making now? And then in part C and D, they go beyond that to thinking, well, what can we do if we want to look to the future in the best possible way? So part C is the formula that would allow them to look into the future. And then part D, they're asking us to do that. Graph profit against price and find the price that maximizes profit. So in other words, we're supposed to just graph pi as a function of p and find the maximum. Now you may recognize what kind of a graph the pi function has here. It's going to be a parabola, so it'll be pretty easy to find the maximum, and in fact you may even know a formula for the maximum, but I'll just follow the directions and we'll graph it. So let me change screens. Okay, so I'm going to use Desmos to graph the parabola that we looked at, we found the formula for in part D. And Desmos is an online graphing calculator. You can use it through the web, and it does a really nice job. I think it has all the features you really need for a calculus class in terms of graphing basic functions and stuff. So the formula that we had in part C was pi as a function of profit was negative 40p squared plus 2200p minus 17,000. And now I will just write this in terms of x's and y's. So often our applied problems are given using other letters, and we should get comfortable, I hope, with using those letters or converting them to x and y if we need to for our calculators. So I'll enter this as y equals negative 40x squared plus 2200x minus 17,000. And you can see at first I don't see anything that looks good. I see like a almost vertical line, and so this doesn't look like a parabola, but I can move my window and I can zoom out, and eventually I'll see, oh, there's two sides of a parabola. I can keep zooming out. It's not a very good scale I've chosen here, and in fact we kind of know what the scale should be, because in part A we knew that the price P was 12, and in part B we knew that the profit there was 3,640. So our window should include 12 and 3,640, and you can see I do have 12 on the x-axis, but I don't have 3,640 on the y-axis, so I should probably change these numbers around. How about for the x's I go from 0 to and I can tell it's like, I don't know, maybe 70 or something, just looking right now on the little bit of my picture that I have left. And then on the y's, again, I can go from 0, and I'm not sure quite how high up it should go. I know one profit was 3,600. Maybe I should be 5,000, maybe 10,000. I'll just make a guess. And you can see 10,000 came pretty close actually, but maybe I should guess a little more. How about 15,000? Oh, that looks great. Okay, so there's the maximum, and I'm just looking for this graphically. So it looks like the maximum is at about 27.5 and 13,250. So I'll write that down on my my other sheet of paper or my PDF, and that'll be my final answer. In fact, I'll go ahead and just make a little graph to remind us what that looked like. Doesn't have to be super accurate. Profit was on the vertical, P was on the horizontal, and the maximum point there that we found was about P equals 27.5. I guess that's dollars. And then the profit was 13,250. And we just did that graphically. I will point out that later in the course, if you don't already know it, we'll find the formulas for the maximum or minimum of parabolas and other functions, and that's one of the main applications of calculus. But that's the end of this example.